Orthogonal Matching Pursuit unveiling the power of sparse regression. The Orthogonal Matching Pursuit (OMP) algorithm in scikit-learn is a powerful tool for sparse linear regression. It stands out in scenarios where you are dealing with high-dimensional data and want to identify a small subset of features that can accurately predict the target variable. This approach offers a concise and interpretable model, especially when faced with a plethora of features. Let's delve into the intricacies of OMP. Core concept. OMP works by iteratively selecting features that are most correlated with the target variable. This selection process is guided by the principle of maximizing the correlation between the selected feature and the residual error, the difference between the predicted and actual values. The algorithm stops when a predetermined number of non-zero coefficients is reached, resulting in a sparse representation of the data where most coefficients are set to 0. Understanding the parameters. 1. Fit intercept, a Boolean parameter that controls whether a constant term bias or intercept is added to the decision function. This is useful when your data has a non-zero baseline or when you want to account for systematic shifts in the target variable. The default value is true. 2. Normalize, a Boolean parameter that determines whether the training data will be normalized before the regression process. Normalization divides each feature by its standard deviation, ensuring that features with different scales are treated equally. This often improves the performance of the algorithm, especially when features have vastly different ranges. The default value is false. 3. N non-zero coefs. This parameter defines the desired number of non-zero entries, i.e., features selected in the solution. If you leave it as non-default, OMP will automatically select 10 of the total number of features. This parameter plays a crucial role in controlling the sparsity of the model. 4. Toll, the tolerance for the stopping condition. This parameter defines the threshold for the residual error. The algorithm stops iterating when the residual error drops below this tolerance. The default value is 1e-4. 5. Precompute, a Boolean or array-like parameter that controls whether precomputations are performed to improve performance. Precomputations are beneficial when dealing with large datasets, high-end targets, or n samples. If set to false default, no precomputations are done. 6. Active set size. This parameter determines the number of features considered in each step for the active set. If none default, all features are considered in each iteration. Increasing this parameter can speed up the algorithm in some cases, but it might come at the cost of accuracy. Exploring the attributes. 1. Core. This attribute stores the coefficients of the features in the decision function. Since OMP promotes sparsity, most of these coefficients will be 0, representing the selected features. 2. Intercept, the independent term in the decision function. This value captures the baseline of the model. 3. Nitter. This attribute stores the number of active set iterations performed by the algorithm. This value indicates the complexity of the model's learning process. 4. Active. This attribute contains the indices of the active features, the features that have been selected by the algorithm. Mastering the methods. 1. Fitx. Why. This method trains the OMP model on the provided training data X and target variable Y. 2. PredictX. This method utilizes the trained model to predict the target variable for the given input data X. 3. Score X. Why. This method calculates and returns the coefficient of determination R2 of the prediction. This metric measures the goodness of fit of the model. 4. Get params. Deep. True. This method retrieves the parameters of the estimator. 5. Set params. This method allows you to set the parameters of the estimator. 6. TransformX. This method transforms the input data X based on the fitted model. 7. MoreTags. This method retrieves a dictionary with additional information about the estimator. Usage scenarios. High-dimensional data OMP shines when handling data with a large number of features, e.g. gene expression data, text data. Feature selection. By identifying the most relevant features, OMP can be used for feature selection, simplifying your model and enhancing its interpretability. Sparse solutions. The sparse nature of OMP's output makes it particularly useful when looking for compact and interpretable models. Advantages. High-dimensional data. It can handle datasets with many features. Sparse solutions provides a sparse representation of the data, leading to more interpretable models. Feature selection can be used for identifying the most relevant features. Disadvantages. Computational complexity. OMP can be computationally demanding for large datasets, as the selection process involves searching through a potentially large number of features. Local optima. The algorithm might converge to a locally optimal solution rather than a globally optimal one. Sensitivity to parameters. The performance of OMP can be sensitive to the choice of a regularization parameter and non-zero coefs. In conclusion, orthogonal matching pursuit is a powerful and versatile tool for sparse linear regression, particularly beneficial in high-dimensional data scenarios. Its ability to identify relevant features and produce sparse models provides a valuable approach for both predictive modeling and feature selection. By understanding its parameters, attributes, and methods, you can effectively harness its capabilities for a wide range of applications.